Hello and welcome to this channel. So, in this video, we are interested to prove the following statement. The statement says that if G is a set of all non-zero real numbers, which is represented as follows: X belongs to R and R is a set of real numbers and X is not equal to 0, right? So non-zero real numbers, if G is such a set, and if if the star operation is defined as A star B is equal to AB by 2, then we need to show that G comma star is an abelian group. Well, the conditions that we need to satisfy are as follows, right? So on the top right corner, you can see that the first condition is the closure, which means that the operation element result belongs to the set G. The second is associativity, right? Which means that which means that if you take three elements or more than three elements, and the operation order of the operation is not really a factor as long as the order of the elements is preserved. Okay, we'll get into that in a minute. Okay, what are the other properties? One is the presence of an identity, right? There should be an identity element such that operation of the identity element with any element returns that element. So there is no change in a particular element. Once we establish that there is an identity, we must prove that for all elements there is an inverse. And finally, since we need to prove that this is an abelian group, right, we need to show that this particular operation is commutative, right? We need to show the property of commutativity. All right, let's get on to work. Fantastic. First property, closure. Now we know that if A and B are non-zero real numbers, right? If A and B are non-zero real numbers, then the product of non-zero real numbers A times B is also a non-zero real number. Since none of the A and B are non-zero, so AB is also non-zero. Since A and B are both real numbers, the product AB is also real number. So AB is a non-zero real number. And since AB is a non-zero real number, if you divide AB by 2, that is also a non-zero and a real number. So since AB by 2 is a non-zero real number, we can say that AB divided by 2 belongs to G, right? So what is the conclusion here? The conclusion here is if you choose arbitrarily A comma B belongs to G, that would imply that the binary operation A star B also belongs to G. That's exactly what the closure property tells us, right? So the closure property is satisfied. Okay, let's move on to show that this particular operation is associative as well. Okay, so let's consider three elements. Let A, B, and C be non-zero real numbers. Then, then let's find out two different uh, operations, right? Let the first operation, let it be A star B star C. Now, we would want that this particular expression be equal to A star B star C. So the uh, operating procedure would be as follows. We will simplify both of these and we'll show that both of these are equal. If they're not equal, well, it will be a contradiction to the problem that we have. Okay, so A star B, the first bracket, according to the definition, is AB by 2, correct? According to the problem, according to the definition of A star B, right? So this is, I have boxed it so that It becomes easy to visualize. And star C, correct? So again, the AB by 2, we have already shown that it is an element of G, right? And that star with C will be this particular box AB by 2 multiplied by C divided by 2. And any high school algebra would tell you that this is ABC by 4. On the other hand, if you look at the last bottom, at the bottom row of your screen, you'll find out another expression A star B star C. We will first conduct the operation which is there in the bracket, and that should give us BC by 2, right? And then this BC by 2 is actually an element of G, because, well, we have already shown that G is satisfies the closure property. Okay, now by definition of the star operation, we get this as A multiplied by BC by 2, whole is entire is divided by 2, and this gives us ABC over 4. And you see that these two operations, both the operations, both the statements give us exactly the same result, right? So the first one and the second one both give us ABC by 4. So this says that, so what do we write down? We write down that if A comma B comma C belongs to G, that implies that A star B, first you do this, then you do the operation with C, will be equal to A star B star C, right? And this proves the associativity. Associativity. This proves the property of associativity. All right, let's move on and check whether there is an inverse or not, right? Whether there is an inverse element or not. Well, before that, we need to check whether there is an identity element. What is the identity element? So we'll suppose that E is the identity element. E is the identity element of G. Now, by the definition of identity element, right? What is the definition of identity element? It says that for for any element A from the group, we shall have A star E to be equal to A, which should be equal to E star A. We'll take forward this particular equation, and this is a special equation. It has got two equal symbols in between, and there is an LHS, there is a mid term like MHS or something, and then there is an RHS. All right. Well, let's do the LHS first. So A star E is AE by 2. Since E is the identity element, we have supposed that E is the identity element of G. It belongs to G. So this is the closure property. This is equal to A, which is equal to EA by 2. Correct? Okay. Then what we do is that we probably multiply the entire equation by 2, right? And then we shall get AE is equal to 2A equals EA, right? We multiply the entire equation by 2. And now we will divide the entire equation by A, right? We'll divide the entire equation by A. How do we do that? We just divide by A over here, divide by A over here, divide by A over here. And is this legal? Yes, it is legal because A is not equal to 0, right? Remember, G is a set with non-zero, non-zero real numbers. So A can never be equal to 0. So we can safely divide any number by A. And once we divide by A, we get E on the left hand side. In the middle, we get 2. And on the right hand side, we get E. So basically, we have found out our identity element. And what is the identity element? The identity element is 2. So E is equal to 2 belongs to G is identity element. Identity element. Fantastic. Let's quickly get into the next property, which is the inverse. These two are extremely related to each other. Okay, great. Oops. Yeah. So this is the fourth property. So what we do is that we'll choose an arbitrary element. A belongs to G, right? And we will suppose, if exists, we do not know whether it exists or not. We have to prove that it exists. So suppose B belongs to G, B the inverse of A. Correct? So we have let that A is an element of G, and we are supposing that B is the inverse of A. So if B is the inverse of A, then there is a condition that it has to satisfy. What is the condition? The condition is A star B should be equal to E, which should be equal to in turn B star A. Correct? Now, in order to simplify this, we know that A and B are both elements of our particular set, particular group actually. Now we are like matured enough in this particular problem to refer to G as a group rather than a set. So A star B is AB divided by 2 because G is a closed group, and this is equal to E, which is equal to 2, right? So we had just found out that E is equal to 2 and B star A is BA by 2. All right. Now what we do is that we multiply the entire equation by 4. So this gives us AB equals 4 equals BA. And again, just as our previous case, we divide this entire equation by A. How are we sure that this is legal? This is legal because A is not equal to 0, right? Okay, cool. Now, what we find out is we find out that B is equal to 4 divided by A, right? And that says us that for all A belongs to the group, the inverse of A is, we can write this as A raised to the power of -1. So this is equal to 4 by A. So the inverse exists, right, for each element. Fantastic. Let's move on to the last property that we need to prove. What is the last property? It is commutativity, right? So we have proved till now, let's recap a little bit. We have proved that the set is closed under this operation. Secondly, we have shown that the operation is associative in the set. The third property is that there is an identity element. And the fourth property is that there is an inverse of each element. So now we have established that G is a group. Right now we need to show that this particular group is an associative, right? Is commutative, right? It's an abelian group. So what we'll do is that we'll let A and B belong to G, right? Now A star B and B star A are the elements that we are interested in. Are these equal? Let's check out. So A star B is AB divided by 2 and B star A is BA divided by 2. So AB divided by 2 is the product of non-zero real numbers, right? And which is divided by 2. So this would of course like be same, so this would be another non-zero real number, right? And similarly the case with the B star A. Now our concern is whether A star B is equal to B star A or not. Now you see, if a is a non-zero real number, right, and b is also a non-zero real number, then we are, what we say is that the product AB is equal to product BA, correct? The product AB divided by 2 shall also be equal to product BA divided by 2. And this in turn shows that A star B is equal to B star A. And that shows that, so that's basically what we wanted to prove, right? So, so, so our relation, so our operation star along with G is an abelian group, because this property over here shows that our particular operation is commutative. Okay, so thanks for watching this video and all the best.